Okay, hello. Uh, so today we will continue our discussion on Fourier analysis, and we will naturally make the transition from the Fourier series to the Fourier transform. So I will there is we will come to this in detail. Yeah. So just a relook at some of the notations which we have been using and which we will use throughout the rest of the course. Okay, of course, when you write a function or a signal x of t, we generally say this is the function of time. This x of t, the signal is a function of time, and this is the time domain representation of the signal. And when you express it in terms of complex exponentials or LTI, eigenfunctions of LTI systems, we generally say it is the spectrum, and then the equivalent representation of the signal is in terms of its spectrum, which is x of e raised to j omega. Okay, so sometimes this x of e raised to j omega, which is the frequency domain representation of this function or of the signal, it may be written as x of e raised to j omega. Sometimes they write it as x of omega, sometimes x of j omega. Okay, so from the context it must be clear, but this is just for you to remember that these are all mostly equivalent. Okay, and then we say that x of t transforms to x of omega. X of t transforms to x of j omega, or x of omega, or x of e raised to j omega. Before we go into the Fourier transform itself, there is one topic which I thought we should just quickly go through, which regards the orthogonality of complex exponentials. So for this, let us look at two sinusoids, x1 of t and x2 of t. x1 of t has a frequency omega 1 and x2 of t has a frequency omega 2. So x1 of t is sine omega 1 t and x2 of t is sine omega 2 t. So now the question is, if you take a linear combination of x1 and x2 such as this, then will the resulting x of t, will it be periodic? Okay, so the answer to that is the x of t will be periodic if omega 1 and omega 2 have common divisors, and the fundamental frequency of the linear combination is the GCD of omega 1 and omega 2. Okay, so this is actually one of the exercise problems in the previous chapter. You can have a look at it. So in chapter 2, I think, yeah. So this was there in the chapter 2. Okay, so basically as an example, if you have sine 2t plus sine pi t, so 2 and pi have no common divisors, so x of t in this case is not periodic. But whereas x of t, if you write minus 2 plus 3 sine 0.6 t and 2.4 cos 2.7 t, now so this is the linear combination where this is frequency is 0, of course, here, and the omega 1 here is 0.6 and the omega 2 here is 2.7. So they have a common divisor, which is 0.3, and so the fundamental frequency of x of t, which is now periodic because they have a common divisor, is the GCD, which is 0.3 radians per second. So just keep this in mind. Then we again will look at we saw the set of harmonically related complex exponentials which had the form phi m of t, which is like this, e raised to j m omega naught t. Okay, when m is equal to 1, we have e raised to j omega naught t, and this we say is the fundamental, and this particular signal in this set where m is equal to 1 has the fundamental frequency, has the fundamental period t, which is equal to 2 pi by omega naught. So this thing which you know, and when you look at when the value of m changes, e raised to j m omega naught t, where m is not equal to 1, Then also this signal is also periodic with a fundamental period t by m, this we saw earlier, and this repeats m times in the time interval of t. We have seen this, right? So these form the set of harmonically related complex exponentials. So one thing to remember is, now if you integrate this over a period t, you will get t when m is equal to 0, or 0 when m is not equal to 0. Okay, so this you can just keep this in mind. So as a homework, you can try to prove this. Okay, it's just 2 steps. Okay, so e raised to j m omega naught t dt integral over a period is equal to t if m is equal to 0, otherwise it is 0. Now in this same context, now when you consider the phi m of t, let's take the complex conjugate of it. Okay, so this is nothing but the e raised to j m omega naught t complex conjugate, which will, if I write it in the rectangular form, I will get cos m omega naught t minus j sin omega m omega naught t, which now is nothing but e raised to minus j m omega naught t. Now what will happen if I do this operation? Go ahead and consider two complex two components of the harmonically related sets. One is with frequency m and the other is the frequency k. So if I integrate this over a period and take dt, integral of this over a period, I will see that the integral becomes t if m is equal to k, and becomes 0 if m is not equal to k. So essentially, e raised to j m omega naught t and e raised to j k omega naught t, where m and k are two integers. Okay, so when m is equal to k, this expression is equal to t, and if m is not equal to k, when this expression is equal to 0. So essentially, so this particular operation, right, this particular operation is a inner product. Okay, this is an inner product. I will explain that in a minute, but so you can consider them as, so the inner product is a kind of generalization of the more familiar dot product. So when you have two vectors in r raised to n, you find out the dot product, right, a dot b, which is ab cos theta. So when you extend vectors to functions, you can extend the idea of a dot product to what is known as a inner product. So a dot product is a particular form of this particular inner product operation. So this is the inner product of these two operations, and you can see that so when m is not equal to k, the inner product between phi m t, phi m and phi k is equal to 0. So just like two vectors are orthogonal, two vectors x and y are orthogonal if the dot product x dot y is equal to 0, in the same way we say that two functions are orthogonal if their inner product is equal to 0. Okay, so basically two different complex exponentials in the harmonically related set are orthogonal because their inner product is equal to 0. So the just as an aside, so consider a complex valued function, two functions f and g in the interval a b. Okay, the inner product is defined as, this is the notation of inner product f g with in angular brackets, it is defined as the integral over a b f of t g star of t dt. Okay, so this is when the functions are complex valued, the inner product is defined as f t g star of t. So you take the first function and the complex conjugate of the second function, do this over the period which we are looking at, which is here in this case it is a b, and then this forms the inner product. So that is essentially what we have done here. Phi m and phi star m, phi m of t and phi star k of t are the two functions which we are looking at, and this is the inner product. Okay, so essentially what this means is that these two complex exponentials, they are having different frequencies or are having different m and k, are orthogonal. So that gives us an so actually there is also a theorem that when you look at it as a vector space of functions, these complex exponentials form what is known as an orthogonal basis. And when you have an orthogonal basis, the when you project one basis over the other, the projection values can be obtained by using the inner product. Sorry, what I meant to say is when you want to represent a function using a linear combination of these orthogonal basis functions, the coefficients of the combination are obtained by finding the inner product between these two functions. This is essentially what is used in the Fourier transform. Okay, so once we touch upon the Fourier transform, maybe I will touch upon this again. Let's see, but just remember this property, that is, whenever you have an orthogonal basis for a vector space or a function space, when you want to represent a new function in terms of these bases, the coefficients of the linear combination can be obtained by using the inner product. Okay, so we will visit that idea again. Okay, so let's come to just relook at one problem which we did in the case of Fourier series, and this was the Fourier series expansion of a periodic square wave. So this is the example, this is the figure 4.1. We saw this in the Fourier series chapter. So this is nothing but a square wave of period t. This is the period, right? And this much portion of which from 0 to t1 is 1, and in one period there are two such portions, here and here, half of this, right? So this is our signal, and this is one period. So we in the Fourier series chapter we developed the Fourier series expansion for this periodic function. Okay, and we saw that this was covered in example 3.5 in the textbook, and the Fourier series coefficients we saw were for k not equal to 0. Okay, for this is k not equal to 0, we saw that ak coefficients were 2 sin k omega naught t1 by k omega naught t. Okay, where this t1 is this t1 and t is this t. Okay, this is t. So these were the Fourier series coefficients, and this is equation 4.1 and also equation 3.44 in the textbook. Okay, so one obvious limitation which we have seen so far is that when we had the Fourier series is existing for periodic signals. Okay, so there are many other signals which are not periodic. Many signals which we want to analyze are not periodic. So how can we have a spectral representation for such signals? So that is where the Fourier transform comes in. Okay, so now if you so if you remember this, so if you see this function again, okay, this particular function, if you see, so what I can do is I can bring the t here. So I got t ak, and then what I do this now, then if the t is not here, this becomes 2 sin omega, 2 sin omega t1 by omega, which is evaluated at k omega naught for various values of k. So you consider this now as a function of omega. Consider this as a function of omega. Okay, so and if you bring the t to this side, t ak becomes nothing but 2 sin omega t1 by omega, which is the same thing here, except that the omega is evaluated only at k omega naught at discrete instance where k has values taking, I mean k takes the value 0, 1, plus or minus 1, plus or minus 2, and so on, and omega naught is the fundamental period of this periodic signal. Okay, so if you see these t ak coefficients are nothing but fixed length samples of this 2 sin of this particular function. So essentially what I mean by that is there is some function here of omega. So what we are taking is from the 0 we are taking samples of this continuous function, and those samples are the TAKs. Okay, those samples are the TAKs. So and so this particular function, that is what we wrote here, 2 sin omega t1 by omega, is the envelope of this TAK. So essentially those samples which we took have the envelope which looks like this. So this is the the envelope is 2 sine omega naught t1 and the samples are the TAKs. Okay. So essentially, so the AKs are nothing but, that is, the Fourier series coefficients of this are nothing but the equally spaced samples of the envelope, of this envelope. Okay. So now one important observation which you can see is, for now coming back to this periodic square wave again. So now suppose you are fixing t, suppose you are fixing t1. Okay, for a given t1, the TAK is independent of t. So if you see here, right, if you see the expression here, this is now, if you see this as a function of omega, now if you are fixing t1, and if you are bringing this t is anyway here, so now this is now this depends only on t1. It is a function of omega, of course, but t1 this does not depend on t. This particular envelope does not depend on t. Okay, so that is what we had seen. This we had seen this in the Fourier series part also. So this is when t is equal to 4t1. So this is my t, this is t, and this is t1. Okay, and so one period is going to be this from here to here. This is one period, and these are the non-zero parts. Right now, when t is equal to 8t1, you still have, this is now t, this is actually double this is 4t1, this is 8t1. So that means this period is double of this period. Okay, so now here also the non-zero parts are the same as what you have here. Okay, so because of these, the TAK values are going to be the same because it depends only on t1. Okay, so the envelope is independent of t. So that is what is shown here. So the envelope depends only on t1, it does not depend on t. So this is for t is equal to 4t1, this is for t is equal to 8t1, and this is for t is equal to 16t1. So the envelope is unchanged, this is still the same, this and this and this are the same. Only thing is, when you get the Fourier series coefficients, so these are, see, 4t1, t is equal to 8t1, and t is equal to 16t1 are different periodic square waves, except that just the t1 part is common in them, but the periods are all different. So if you, all of them will have its own Fourier series. So you can see that the Fourier series coefficients here are nothing but, like we said, the samples of this envelope. The envelope is taken at regular samples of 2 pi by t, which is your omega naught. Right? This is omega naught when k is equal to 0, omega naught when k is equal to 1, omega naught when k is equal to 2, and so on. This is 0, omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on. Okay, so this is for 4t1. Now when you have for 8t1, it is the envelope is the same, except that now the sampling interval becomes half, becomes smaller. Okay, so and similarly when t is equal to 16t1, the sampling the size between the samples, or the gap between the samples, becomes even smaller. So essentially what is happening is, as your t is increasing, the space between the samples gets smaller and smaller and smaller. Okay, so as t increases, the fundamental frequency omega naught, which is 2 pi by t, and that decreases as t increases. So essentially it means that the envelope is sampled more and more densely as t becomes larger and larger. And the other thing which happens is, as t is becoming larger and larger, this is now 2t, now t becomes larger and larger. Essentially this periodic signal becomes aperiodic. So it no longer becomes periodic when t tends to infinity. Okay, so that means the repetition happens at time is equal to infinity. So it is a non-periodic signal. So essentially this, so in the limiting sense, the Fourier series coefficients, that is the scaled, because here we have a t here, it is a TAK. So these Fourier series coefficients, as t becomes infinite, the Fourier series coefficients become the envelope function. So the closely spaced samples become more and more close, and finally it gets every point in the envelope, and that is how the discrete Fourier series becomes the continuous Fourier transform. Okay. So there is a derivation in the book which shows how formally how the Fourier transform comes from the Fourier series by essentially extending this idea and doing the derivation. You can have a look at it. It is pretty straightforward, but we will skip the derivation for the moment, and then we will see the final result, that is essentially the Fourier transform pair, okay, which is essentially just like in the Fourier series. We have two expressions. We have the synthesis equation and the analysis equation, where the synthesis equation gives the expression of x of t in terms of the Fourier series coefficients, and the analysis equation gives the Fourier transform coefficients by doing this operation on the x of t. So let us see this with respect to the Fourier series, which we are more familiar with. Okay. So we have again in the Fourier series, this is equation number 3.38, we have the synthesis formula where x of t is synthesized, or it's created as a linear combination of complex exponentials, right? For k varies from minus infinity to infinity, but k takes values which are integers, they take discrete values, and these are all harmonically related complex exponentials, and ak are the coefficients of the linear combination, and that will give you x of t. And the analysis equation, which was giving you the Fourier series coefficients. So if you take x of t and then e raised to minus j k omega naught t, that is by taking, so if you relate it to the inner product which I mentioned earlier, so this is nothing but we are taking the inner product of x of t and e raised to j k omega naught t. So when you take the complex conjugate, that is why this minus j is becoming minus j. So essentially what is do, so if you remember what I said if you have a set of, you have an orthogonal basis, the coefficients to represent any signal using that basis, the coefficients of the linear combination can be obtained by taking the inner product of the function you want to represent and each of the basis vectors. Okay. So these AKs form essentially the coefficients of the expansion of these form the coefficients of the representation of xt in these bases. Okay. So if you look at it from this point of view, the Fourier series expression becomes very clear. So now if you compare this with this, you can see that you can naturally make out the difference. This is the synthesis equation, this is the synthesis equation. You are going to represent x of t. Here x of t is a periodic function, whereas here x of t need not be periodic, is not periodic. Okay. So there is a 1 by 2 pi scaling factor, forget that for the time being. Now here it is a linear combination, a discrete linear combination, but here the basis vectors here are harmonically related complex exponentials, but here the basis vectors here are not harmonically related, they are in fact over all omega. It is a continuum of frequencies. Okay, this is x of j, and this forms the linear combination, this forms the coefficient of the linear combination. So essentially what we are doing in the synthesis is that we are expressing the x of t in terms of a continuous linear combination, where these are the linear combination coefficients, and this is a continuum of omegas, not discrete k omega naughts, but continuum of omega, that is why we have a d omega. And similarly in the analysis equation, we are taking the inner product between xt and e raised to j k omega naught t, where k omega naught t is the harmonic component. But here in this case, here we do not have discrete k's, we have a continuum of omega. So again we are taking the inner product between x of t and e raised to j omega t, and we are doing it over all t. This will give me the expression for the x of j omega, which is essentially the coefficient which we have here. Okay. So you can see that there is a parallel between them, they are essentially very similar. Okay. So a periodic signal, the Fourier series coefficients occur at a continuum of frequencies, and where the amplitude is nothing but x of j omega d omega by 2 pi. Essentially it is this one. So if you compare this with this, the linear combination here is x of j omega d omega by 2 pi. Okay, that is same as the that's taking the place of ak here. So now okay, this part we can skip for the moment. Okay, now let us talk about convergence of the Fourier transform. So we had talked about convergence when we studied Fourier series, and we saw that there were several things involved in the convergence. So those same things happen here also. So let us look at the synthesis equation, which is this one here, right? We are going to represent x of t in terms of its Fourier transform. So let x of j omega be the Fourier transform, and we are representing the approximation x tilde of t, which is an approximation to x of t. So this is the synthesis equation. These are the Fourier series Fourier's transform coefficients. We are multiplying by the basis vectors, and we are getting my representation x tilde of t. So now the question is, how good is x tilde of t to represent x of t? So as in the case of Fourier series, what we do is we determine an error, which is the difference between x of t and x tilde of t and x of t, and in that case we define the energy of the error. Okay, energy of the error is the NR over minus infinity to plus infinity dt. So here, just like we did in the Fourier series, right, for different types of for different situations we define different types of convergence. And when we have this kind of energy of the error, we are talking about convergence in the mean. Okay, so we resort to this convergence in the mean when there are discontinuities in x of t. Just like how we saw it in the Fourier series case, whenever there was a discontinuity in the signal, like for example the periodic square wave, we had to resort to convergence in the mean, because at the points of discontinuities the Fourier series were not converging in the uniform way. So we had to resort to convergence in the mean. Similarly, in this case also, if there are discontinuities in the signal, we will have to refer to we will look at convergence in the mean. And like in the case of the Fourier series, a sufficient condition for convergence in the mean is that the x of t, the signal which you are going to represent, should be square integrable. So essentially what I mean to say is that, so if x of t, if you want to, if you are synthesizing x of t using its Fourier transform coefficients, a sufficient condition for the synthesis equation to converge to x tilde of t in the mean is that x of t must be square integrable. Okay, so this was the same condition which we saw in the Fourier series case. In addition, there are the Dirichlet conditions, which this very similar, which is the same thing for the Fourier series. X of t must be absolutely in x of t must be absolutely integrable, x of t dt less than 0. This was one sufficient condition which we saw, very similar, the same thing which we saw for the Fourier series. So if it is absolutely integrable, then this is one sufficient condition for the Fourier transform coefficients to be bounded. So this was one condition. X of t must also have a finite number of maxima and minima in a finite interval, and x of t must have a finite number of must have only a finite number of discontinuities. Okay, so these were the same Dirichlet conditions which we saw in the Fourier series case. So if the signal x of t, which we are trying to represent using the Fourier transform by using the inverse Fourier transform or the synthesis equation of the Fourier transform, if the signal satisfies these three conditions and has no discontinuities, then the synthesis equation which we saw here, synthesis equation will converge to, or that is your x tilde of t will converge to x of t uniformly. But if there are discontinuities in x of t and x of t is square integrable, then the x tilde of t will converge to x of t in the mean. That means there may be isolated portions where the x of t and x tilde of t don't match. So, so those are the two conditions which we saw. I mean, like, these are exact parallels with the Fourier transform and the Fourier series. Now, there is actually one more case which we have not really looked at in the Fourier series case. This is the case of periodic signals over an infinite interval. So, in the Fourier series, what we saw was there was a particular period at period t, and we looked at the Fourier series convergence only within that period. Okay, so we were interested only in the period, the periodic function, and we were restricting our analysis only to one period. Okay, but there may be other functions, like for example sinusoids, which exist from minus infinity to plus infinity. So this is minus infinity and this exists to plus infinity. So sinusoids exist from t equal to minus infinity and t equal to plus infinity. So if you want to analyze the sinusoid over the entire interval, infinite interval between minus infinity to plus infinity, we cannot apply Fourier series or Fourier transform, because a sinusoid like this is neither square integrable or absolutely integrable. So neither this condition nor this condition is satisfied when you are looking at a periodic signal which has an infinite interval. Okay, so it is neither square integrable nor it is absolutely integrable. So we have to resort to some other way to represent, because we want to have Fourier transforms for such signals also. So for that, for such signals, for periodic signals over an infinite time, we will use delta functions, and we will represent the Fourier transform using delta functions. We will see that later when we study. Now we will look at some examples from the textbook. These are very illustrative examples, so that is why I have chosen them. So example 4.1. So now x of t is e raised to minus 80 ut, okay, which is nothing but a function like this for a is greater than 0. So if you apply the analysis formula, you get your x of j omega, which is 1 by a of j omega, a is greater than 0, and this is of course a complex number. X of j omega here is complex, so you will have to plot the magnitude and the phase separately, and of course this is j omega. Now the Fourier transform is seen as a function of omega. It's a function of omega. So magnitude is like this and the phase is like this. So is this a low pass filter or a high pass filter? So if you see the frequency response, or if you see the frequency analysis, you can see that it is a low pass filter, essentially because it allows values around 0 frequency to pass with high without much change, or with it amplifies these parts and attenuates these parts, which are high frequencies are from here, right? These are the high frequencies, these are the low frequencies, these are the high frequencies. High frequencies are the attenuation is, the gain is cut down. Now we will see e raised to the second example, example 4.2. x of t is e raised to minus absolute value t. So this function looks like this. So now you can see that now if you apply the Fourier transform, if you find out the Fourier transform looks like this. And of course, since this is a signal which is real and which is even, x of t is real and even, the Fourier transform will also be real and even. Okay, so this comes from the Fourier transform properties. This is real and even. Another example 4.3 from the book, where what is the Fourier transform of delta function? X of t is equal to del of t. So apply again the analysis formulation. When you do this by using the shifting property, you will get that this is equal to 1. Okay, so essentially what it means that a delta function has all frequencies. So essentially the frequency of the delta, the frequency response of the delta function looks like this, where this is your omega and all frequencies are present with equal amplitude. Okay, every frequency is present in a delta function. Another example, example 4.4. This is again the periodic square wave which we saw earlier. X of t is 1, so from between 0 to t1 it is 1, otherwise it is 0. And so this is essentially not periodic, this is a non-periodic signal. It is the square periodic square wave where the period is equal to infinity. Okay, so if you apply the Fourier transform, if you apply the synthesis, the analysis formulation, you will get 2 sine omega t1 by omega, and this looks like this. Okay, so this, so if you plot this function, this is going to be a real function because our signal here is real and even. So our Fourier transform will also be real and even. So Fourier transform looks like this, and if you plot this function, it looks like this. Okay, so this type of function is known as a sinc function. We will see this again in the next example. But of course, now if you consider the x of t is not a continuous function. It has a discontinuity at minus t1 and plus t1, right? So if you want to synthesize your x of t using the Fourier transform by using these sinc functions, and if you apply it into the inverse Fourier transform or the synthesis formula, how does the inverse Fourier transform of this come to this? Okay, so this function is square integrable, and it has a discontinuity. So we have to use square. I mean, it is square integrable, and hence the synthesis equation, this particular synthesis equation, when you put it here, this is your x of j omega. It converges in the mean to xt. Okay, so essentially what that means is, if you take the inverse Fourier transform, which is 1 by 2 pi from, let's say, from minus omega to omega, e raised to, this is the synthesis formulation, as omega tends to infinity, how does the inverse, or how does the synthesis of this, where these are the coefficients, come back to this? So because it is convergence in the mean, you will see that the Gibbs phenomenon which we saw earlier is present here also. So as you add more and more terms, this will become your x tilde of t, which is the approximation to x of t, and your x tilde of t will have ripples here, because at the discontinuities the synthesis equation, your x tilde of t, which is same as this, will not exactly match x of t. There are isolated points where it will not match, and this is the reason for the Gibbs phenomenon. Another example, example 4.5. This is, now consider x of t whose Fourier transform is given here. Okay, so the Fourier transform is this. So in the previous example, this was my time domain signal, which is a square pulse in the time domain. So now I am giving you the square pulse as the Fourier transform. So this is the Fourier transform. What is the x of t, which has this Fourier transform? Okay, so this is, there are a particular w, minus w and w in the omega axis, where the discontinuity occurs in this x of j omega. So again, this is a even and real. So the Fourier transform of this will also be even and real and even. This comes from the Fourier transform property. And again, when you have you get the same kind of the sinc function which you have here is what you have here also. Okay, so essentially what this means is, this is what is known as the duality property. So a square pulse transforms to the sinc, and the sinc transforms to the square pulse. So this could be in time, this could be in frequency. I mean, if this is in time, this is in frequency. If this is in time, this is in frequency. Okay, so there are these duality properties which will sometimes help us to solve problems. So no matter what domain you are, the Fourier transform can have a particular shape. The Fourier transform pairs will have a particular shape, that is, the square will transform to a sinc and sinc will transform to a square and vice versa. Okay. So, this could be in, like I said, time or in frequency, this could also be in time or frequency. Okay. So, generally the sinc function has the form sin a theta by b theta, because this, if you put this value into the inverse Fourier transform and put it in this, the inverse Fourier transform is nothing but the synthesis formulation, and when you get the x of t, you get 1 by 2 pi, and you do this over minus w to plus w e raised to j omega t d omega, you get sin omega t by pi t. So, generally sinc functions have the form sin a theta by b theta, or in general one way to represent the sinc is sinc of theta, which is sin pi theta by pi theta. And so, this is how pi theta by pi theta looks like. So, just to conclude, what we will see is, we will look at some relationships between sinc and the square pulse. So, these figures show various values of various transform pairs. Okay. So, there is a sinc in time, and this is the Fourier transform of this particular, this is the Fourier transform. Okay. So, you can see that here the transform is the square pulse, this is all omega axis, and these are the corresponding x of t's. So, this x of t has this Fourier transform, this x of t has this Fourier transform, this x of t has this Fourier transform. Now, you can see that as the width in the transform domain increases, okay, if the width is high, the time domain representation is narrow. If the width becomes little lesser, the time domain representation becomes little broader, and if the width of the transform becomes very narrow, the width of the time domain becomes more and more broad. So, as it gets narrower and narrower here in one domain, it becomes broader and broader in the other domain. So, whether now this was in particular, this was in time and this was in frequency, but if this was in frequency and if this was in time, you will still get the same behavior. That is, more wide in one domain becomes narrower in the other domain, the sinc, and more broader in one domain becomes narrower in the other domain. Okay. So, this kind of trade-off is there. Width narrower in one becomes wider in the other. So, this we will see later when we see the Fourier transform properties. Okay. So, please read these sections from the textbook. Fine. Thank you.